Hello everyone, and welcome to the bettercrypto.org training session. My name is Vincent Chernow. I work for Abusix, and I'm one of the co-chairs of the training committee. I'm honored today to welcome David Durvaux, one of the initial members of the crypto.org organization, and also a security analyst at cert.be in Belgium. At cert.be, David helped to develop and deploy the cert's new infrastructure based on their open source project, Abuse Helper. And David?
Good evening, everybody. So, why the bettercrypto project? So the project was started 1 year ago, and mostly due to that. At least that's the funny way to say it. So there is some truth in there. So, of course, there is not only the NSA that is listening. It can be basically anybody. But the Snowden revelation about what the NSA is doing was a sort of wake-up for some people to just realize that somebody can listen communication. They can listen SMSs, emails, internet communication, chat, whatever they want, and that you are willing to protect yourself with your communication, your data. And NSA is doing that, criminals sometimes too. And then the idea is, that's the answer basically to the NSA. You can protect your data, and the idea of the guide was to really help system administrators to correctly set up cryptography on their system, because we realized that sometimes it's really difficult. There's a lot of terms, algorithms, and they don't know how to configure them correctly. That's mostly the reason. That's basically your fight. Protect your data if you're willing to protect them, and otherwise give them if you want it, but have the choice. So the project was written by quite a long list of people from different horizons. You have people from different universities in Australia and Germany. You have people from CERT, I think mostly Australia and Belgium right now, a few private companies. So we have in there people that really know how algorithms work because they are cryptographers. You have people that have the point of view of CERT doing incident handling, and you have people that are system administrators and know how to configure the system. And with all those profiles, we try to build a guide, a cookbook that you can use and then also contribute to if you want. So today, I'm willing to cover the following points. So briefly, some pieces of history, because cryptography is not new, and it's really hard, actually. Then introduce the project itself. Go quickly to some cryptography in the nutshell, sort of introduction to some concept, not too deeply, because I think if you already know them, it's just boring, and if you don't know, we don't have enough time anyway. Go to some practical settings and show what's really the result. Show some testing tools, and then go to a demo with GPG and show how you can do cryptography and just have a demo. As I mentioned, cryptography is not new. And actually, the picture is from a book, which is really nice if you want to go deeper in that. But we have traces of cryptography at the time of Caesar. And he was simply using a piece of wood, then putting a sheet of paper around the wood, the piece of wood, turning in, and then you have a simple shift of letters. That was quite simple. For instance, A become E, B become F, and so on. And that's really easy to break, but at the time, nearly 2,000 years ago, that was the way they do it. It was improved later, and it was visionary cipher when you use multiple operations like that, but at the end, that was maybe the first process of cryptography. And then later, it has a huge impact for Mary Queen of Scots when she basically was executed because her code was broken. So she was trying to get back the kingdom of England, and then they discovered some letter that she exchanged, broke the code, and then found evidence that she was involved in some attempt to get back the crown of England, and for that she lose her head. So really bad to have bad use of cryptography with impressive impact. Then later you have that machine, maybe you recognize it, which is the Enigma machine, which was used by the Germans during the Second World War. And that machine is interesting because she was broken by the first computer, which was built in England by, I forget the name, Alan Turing, thank you. And so when the machine was suddenly broken, it was a bad time for the U-boat seller because when they come out, you had to destroy off the allied that were just waiting for them and basically killing all of them. So bad time for the German army when their machine was broken. But so again, when cryptography is broken, it could have impact. But the Better Crypto project itself. So why we have done that is firstly because when we speak about crypto, it's basically mathematics, and it's most of the time advanced mathematics. So there are not a lot of people that really understand every piece of those mathematics, and it's really difficult. In some case, I remember university time where even the teacher says that he even not understand every piece of them. So even good cryptographer can say that they don't understand everything. So from a system administrator point of view, you cannot ask them to understand every piece of it and do choice by understanding how algorithm works. So difficult concept. There are a lot of algorithms. Difficult to know which algorithm is okay and which algorithm could be broken. And then there are also a lot of parameters. So a good algorithm with bad parameters can also be broken. And if you take everything in account, all this in account, then you really need someone that say, okay, you have those algorithms are considered as good, you can use them, and you should use those parameters to have a correct implementation, a correct use of those algorithms. And that's the reason of the paper itself. And it's why we mix different perspectives, different point of view. And I will show you later, but if you still look at the mailing list right now, we still have a lot of discussion on some topics and some ciphers. So it's not that easy, but we try to push something practical. So the idea, that's difficult for some administrators, and then we try to write a cookbook, and that's the Better Crypto project. It's not more than a cookbook, that's a cookbook, that's it. So it's not a crypto course, because that's not the idea. There are already a lot of good books, so if you want a course, then you should go to a book which is a course, and it's not a static document. The last point is really important for us. We are trying to have a state-of-the-art document now, and we want to continue to update the document as it will evolve. We know that some algorithms are coming, some algorithm will be broken sooner or later. That's part of the game. If you look at, for instance, private-public cryptography, basically it's rely on some principle that will be broken by quantum computer when it will come out. So probably stuff will change in a few years, 10 years, 20 years, don't know. But a static document is useless. It needs to evolve, and we will try to keep document up to date. In brief, we have done that. That's a community effort. So we are, as you see, quite a long list of people that wrote part of the document. We try to use best practices coming from different documents. Everything is in the reference afterward in the document. We are still continuing to work on it. If you look at the latest version on the website, you will see that it's still written draft on it. It's nearly about 100 pages right now, so quite a long document, but still a draft. With people from different expertise and knowledge. And everything is open source. So it's a LaTeX document. You can take the source, you can contribute to it, and you can give it back. You can also use it. That's the idea. And it's open to suggestion and comment. We are really willing to get back suggestion and comment. That's really important for us. So if you look at the document itself, we basically have two parts in the document. The first part is really configuration. So you have a list of services like Apache, and then a configuration we propose and we recommend. Then you have a second part, which is the theory. And the goal of that theoretical part is to explain why we choose certain settings in the first part. And we also do that because we are pushing transparency. So we want to explain why we choose certain setting and just have a relation between what we recommend as configuration for Apache, for instance, and stuff we recommend in the theory or we pick from different type of documents. And we also try to cover as much tool as possible. There are still some tools that are missing right now, but we are trying to extend, and again, if you can contribute, it's welcome. To use the guide, we have built some, in quite pretty bizarre way, document as the theories after the practical settings. probably you have expected the opposite. But so there is basically the beginning of the document and some introduction. And the idea is, depending on the time you have, you can directly go to practical settings. So if you have no time, you need to configure some services, you can simply copy-paste configuration, and it should work. We document each time which version we use and which version we tested, but you can simply copy-paste. Ideally, if you do that, it's really good. It's probably the best. It's going back to theory afterward. Just read why we have picked some specific parameters, and then go back again to practical settings. And you will probably understand why certain settings were enabled, certain are going disabled, explicitly or not, and just really understand why everything is chosen, and maybe criticize, and maybe decide by yourself that some settings are not correct or not valid for you, because not compatible with some client, or you need something else, and then you can adapt, but you can read it in both ways. If you have time, you can directly go to theory, then look what we recommend, why, and then go to practical settings afterward. And you can so just play with the document as you want. Everything, every references in the appendix, so you can afterward also review and just check that we didn't do mistakes. It's also still possible. Okay, you had any question to know? Okay, great. We'll go to crypto in a nutshell. So basically, when we speak about crypto, you have two types of goals. I mean, two big types of goals. The first one is you want to protect the content of the message. So you send a message to somebody, and then you are willing that the content of that message is unreadable for someone that would just listen to the message or just eavesdrop it. So you want to send a message to, let's say, Alice wants to send a message to Bob. Only Bob should be able to read the message. And it's so you have then two types of protection. The first one is not being able to read the message, and then not being able to change the message. So it's two types of different protection. But you also want some time to identify who wrote the message and be sure that if you are Bob, it's really Alice that sent you the message. And those type of goals could be combined to just be sure that the message is intact, was not modified, the message was not read by anybody, and that it was really sent by the one that is supposed to send the message. Then there are two families of algorithms. The first one is the symmetric cryptography. The idea, the idea is that you share a key. So both the green guy and the blue guy have the same key. And when they need to send a message, they pick a very secret message, cipher the message with the key, and send the cipher text to the blue guy, and the blue guy is able to read it thanks to the key. The issue there is you need to exchange the key. And that's really the problem with that type of algorithm. If you are trying to exchange a message from Europe to US, which is quite common now, exchanging the key could be an issue. You will not take a plane to just give the key. If you reuse the key, then you know that if at some point the key gets compromised, or the message also gets compromised. And so you have a lot of issues around symmetric cryptography on how to exchange the key. The good point with symmetric cryptography is it's efficient. So if you look at AES, it's really quick compared to other type of algorithm, but you need a way to exchange a key. The other family is asymmetric cryptography. That's really nice, as you didn't have that issue with key, because blue, if I want to send a message to blue, blue will have actually two keys, a public key and a private key. And you only need to keep secret the private key. The public key, you can publish it on his Facebook page, his Twitter account, his web page, wherever you want. It doesn't matter. If green wants to send a message to blue, you can pick the public key, the place where the public key is supposed to be, cipher the message with the public key, and only the blue guy will be able to read the message. So the issue of exchanging the key is not there anymore. Then you have two new issues, unfortunately. First, it's slower, so it has a cost in terms of computer resources. And you also you need to trust the public key, because it can be published on a website. How can you trust that website? Is it really the key of blue? And then you need to fix that somehow, so I'm going to try to fix that. But at least you have a way to just cipher a message, and you didn't care about protecting the public key. It is nonsense, you can just publish it. A nice feature of asymmetric cryptography is signing. If you use it the other way around, if blue wants to check that it's really green that sent out the message, actually green can sign the message using the same algorithm, same type of crypto. It just generates hashes and then cipher it with its own private key. And with the public key of green, blue is able to just do the opposite operation and check that both hashes matches, basically. So that's really nice, as you have no mean to check that green, or at least the one that owned the private key of green, really wrote the message. And yes, the fact that the one that owned the green key, it's important, because if you lose your key, then anybody else can sign. It's like if you lose your, in Belgium we have ID card with a smart card, basically. If you lose a card, someone is able to sign with your card if you have the PIN code. Then, as usual, you need to protect the private key, but at least, as long as the private key is protected, you have that feature. So, if we go back to symmetric cryptography, I mentioned that the issue we have is how to exchange the key. And we're again helped by the algorithm behind public and private key. I won't go to the math there. I just keep the slide on that. The idea there, and now we just keep the ideas. You have Green and Bob, and at some point they want to share a secret. And they want to share a secret on a channel and that someone could listen. So you want to be sure that at the end, they both have the secret, which is S at the end. And if somebody listens, is not able to retrieve. So the element algorithm is widely used, you will see later, to just do that. So the fact they both have a secret at the beginning, they have public information. So as you see, Green has a secret A, public information P and G. He will send the public information to B, to the blue guy. It doesn't matter if someone listens, it's public. And then the blue is doing some maths with that, and Green do some maths with them. And you see the same type of formula. And then they exchange the result of the maths, so the big B and the capital A. And by doing again some maths, they achieve with the same secret. So you can prove that if you want, or you need to trust me, but it works. So at the end, they end up both with the secret S, which could be used as a secret key for symmetric cryptography. So you now fix the problem of symmetric cryptography. You have efficient way to cipher and efficient way to exchange the key, which is quite interesting now. But, so by default, when you use Diffie element, you always use the same public and private key. If you do that, if the information gets compromised at some point, you're able to uncipher messages that were sent previously, and if you didn't notice message, you will send later. So it's why there is a mode for Diffie element, which is called ephemeral mode, where both sides, blue and green, generate each time a new key. And by doing so, you just grab new key at each session, and then you're able to you have new key basically each time that you communicate. And so like that, if someone get the message and get the key at some point, is only able to just uncipher the messages that were sent at that moment. Previously and later, not, because it's new other key. You need to compromise all the keys and all the session, basically, which is more complicated than only one. So the next stuff I want to introduce is hashing. So the idea behind hashing is it's basically used when you need to sign. Signing by sending big piece of text is really not convenient. So hashing, the idea is you take a long text, you put it in a box, which is a hash algorithm, and you give out a fixed length output, which is supposed to be quite unique. Quite unique because there is a probability, as you have big set as input, a limited set at output, there is always a chance that you have a collision. And by picking the correct algorithm, the chance is really, really low, and you can deal with it. If you take SHA-1, the probability is, there is too many figures to just spell them, but you see that's a quite big figures. So you can suspect the probability is quite low. When we say collision, collision is basically two different inputs that produce the same output. If you use hashing to sign, it's important to pick up a good algorithm. If you look at, for example, MD5, there are some techniques that are now used to produce collision. So there is a way to produce collision. So you should not use MD5 to authenticate message. You can leave MD5 for other stuff, but probably not for crypto. recommend to use more than SHA-1, but you see the probability with SHA-1 is quite low. Again, there are some papers that tend to prove that there's some possibility to also produce a collision there. Then TLS, I won't go deeply to the handshake. So the schema on the left side is the handshake. Basically, TLS pick up everything, which is quite nice. So they start with the hello message where you exchange random number at Cipher Suite. So both sides exchange Cipher Suite, the support. They also can authenticate themselves. So again, thanks to public-private cryptography, they can just validate certificate and prove that blue is blue, green is green. And then at some point, they send a message, send Cipher Suite, and basically just afterward, the first message finished. They switch to a new algorithm with key and secret that were discussed before. And that's really nice because if you look, you can start with public-private cryptography, which is not really, really efficient or less efficient than symmetric cryptography. Then you can discuss which algorithm you want to use, which parameters, and then at some point switch to symmetric cryptography you want to, and then go to efficient way to Cipher. And it's typically what TLS does. And it uses basically all the stuff we have seen before, so Diffie-Hellman and certificate and signing and so on. So for what secrecy motivation, we already speak a little bit about it. So the idea is some people, the three-letter agency in some country, do store all the traffic. And they wait that you use the same key to be able to uncipher everything. That's basically the idea. So if you use these techniques, and that's the reason to just change the key often, then you can achieve the fact that the message that is sent today will use another key. Sorry, I will go back. So the idea there is, you know that they store all the traffic, and you want that your traffic being protected in the future and in the past. So by using new key pair each time, you try to achieve that goal, and that was the reason typically for Diffie-Hellman, ephemeral Diffie-Hellman, the key has changed all the time, just to be sure that keys are not reused, and that if they got the key at some point, they're only able to decrypt a piece of the traffic, not everything. Yeah. The drawing is quite nice if you look at it, and quite true also because breaking long key algorithm is quite complicated, but there is always the fact that if you got the key at some point, then you can uncipher. So you should really emphasize that you need to protect your key. So perfect forward secrecy, the way to do it is Diffie-Hellman ephemeral, so as already mentioned. And using private key, I said private key only for authentication, not later. And ideally change the key every period of time, so every week, every X months, just to be sure that key are not reused too long. The good point is it's really secure against future attack. The bad point is it costs. As generating key, you need randomness, need entropy of the system, took time, took computer power, and you also need to each time generate key, exchange the key, and it has a cost. The last concept I want to introduce is the stream and the block ciphers. So we'll see that you have two families of algorithm, at least symmetric algorithm, the stream cipher and the block ciphers. So the stream cipher, the idea is you have you generate an infinite key streams. So the key is as long as the message you want to cipher. The problem is it's really difficult to correctly use, and you tend to reuse the key. But it's fast. And really, it's basically RC4, which is used there, and it's a broken algorithm. So we won't speak really about stream cipher. And we will mostly use block cipher, which are more safe. The idea is you use a fixed key size, and you cipher by block. And if the block is not long enough, so you just split your message in fixed size block. If the piece of the message is not long enough, you just add some padding at the end to have the correct size. So dummy data at the end of the message, and then cipher by block and send block. And it could include what we call HMAC, so integrity protection. You can detect that the block was corrupted on the wire, and you can, as for in transmission, know that the message was corrupted. So you have nice property with block ciphers. On the key generation side, randomness is really randomness is really, really, really important. The problem is now we are dealing with quite a lot of embedded devices, like smartphones, tablets, and so on, and they tend to generate key at boot time or close to boot time and use other properties like the clock to generate randomness. And if you do that, they just basically start by 0 predictable value, and there are no issues with the randomness or embedded device. So having a good source of randomness is important as it guarantees the quality of the key. So I'm sorry for the schema. It seems to be quite slow. It just shows for SSH and TLS the repeated key, and the blue part, it just shows that you have 60% of repeated key in TLS, in some TLS scan, and it just shows that if you have bad randomness, you can end up with the same key. If you look at SSH, you can authenticate with keys. If you have the same key, basically you can authenticate on servers that are not your servers, and that's an issue. And it unfortunately happens. You have some SSH servers that are not using unique key, but key that you can find on other servers. And that's not good for the owner of those servers. And you find that typically on small devices or small cards that have bad sources of randomness. So it's really the idea of take care of the randomness. You also see that some sort of randomness was supposed to be broken and backdoored and is now not used anymore in RSA. But at some point, some RSA key were using bad source of randomness. Intel now recommend to use system entropy. And they do not trust anymore some chips on the motherboard. Basically, there was some discussion about, do the chips really produce randomness, or is the randomness predictable? Do you trust vendors to give correct source of randomness? And you can also you should basically mix all the sources you have to try to have as much as possible a good quality of randomness when you need random data, just to be sure that you have really random data. FGE is a nice project and a nice tool. And then by regenerating the key from time to time, you also try like that to have keys that are not predictable. So it's always a good practice to just tend to regenerate key from time to time, yeah, and then change your key, like you change your password, maybe change your key from time to time. I will not go longer on the theoretical side. Probably if you want to have more, I know that it's maybe not enough for some of you, maybe it's already too much. If you want to have more, there are a lot of really good books. I can recommend some if you want afterward. That's really nice to just understand how all this works, but yeah, I want to not go too deeply and avoid that you all fall asleep.